Hey guys, welcome to recitation number 15. Well, just like I said this one in the lecture, we will solve only problems in recitations, and we will solve problems from the worksheet number 4. Well, worksheet number 4 will involve only real analysis questions such as sequences in series, continuity, differentiability, integrability, even functions of several variables. And at the end, you will see even differential equations. So now we will solve some problems involving integrals. And this will involve more computational integral or some things that we will involving only very rudimentary things, like we can use only very basic things of the integrals. Nothing special. All right, so the first, let's dive in directly, and the first question that I would like to solve is the following problem. So it's a quite an easy one. So this was problem, I don't know the number. I'll look it up. Problem. Anyway, this was a Putnam problem, right? This was Putnam B1 in 1987. Just like I said, it's a pretty easy problem. And the statement is the following. So it's very simple. Evaluate the integral, let's call this I, from 2 to 4 of this function, square root of natural log of 9 minus x over square root of natural log of 9 minus x plus square root of L natural log of 3 plus x, right? All right, dx. That's the first problem in this recitation. So, well, it's a pretty standard problem, I would say, because, well, if you look inside the integral, the expressions, the expression inside the integral looks very complicated at first, right? So we have a ratio, we have the square root, we have the log, and so on. So at first, you might be tempted to do some kind of a conjugate thing, so that, I don't know, maybe you can make the denominator look a little bit better than it is now. All right, you can try that. But also, if you look at those expressions, the quantity inside the natural log, so as you can see, you have here 9 minus x, right, and 3 plus x. And actually, there is a relationship between these two. So let's make this, let's point out this remark. So as x changes from 2 to 4, right? 9 minus x changes from 7 to 5, right? And 3 plus x changes from 5 to 7. Wow. Right? That's pretty obvious to see. So we'd like to use this. Maybe we can see some kind of a change of variables, like a U substitution. All right, so if we look at these two functions, right? Another remark is that if we take these two functions, right? So if we take the functions, let's say, and let's denote them by, let's say f of x is the square root of the natural log of 9 minus x, and g of x is the square root of log of 3 plus x. Well, of course, both of them are defined on their the domain of definition and so on. I don't want to get into that. It's if we take these two functions, it's pretty easy to see that then one can observe that the graphs of these two functions are symmetric. And that's an important word here, are symmetric, right? On the interval to 4. And of course, close at both 2 and 4. So maybe that could give us a hint of a change of variables. So maybe you can take change of variables. So we can perform the U substitution in the following way. So maybe take this U to be, X is 6 minus U. All right, so let's see, what do we have? So if we do this substitution, then we have so we have that this integral I. So now we're gonna when x is 2, y will be 2, right? Sorry, y will be 4. And when x is 4, y will be 2. So we will have that the integral from 2 to 4 of the square root of the natural log of 9 minus x will be 3 plus, y here, u is u. So this would be 3 plus u. All right. Here downstairs, what do we have? So we have the square root of the natural log of 3 plus u plus the square root of natural log of 9 minus u. Great. And now let's be careful here, du. Okay. Yeah, we'll have a minus here. So you see, it should have been the integral from 4 to 2, but here we have a negative du. So we put that outside and then you swap the bounds. So we'll get this. Well, I hope I jumped this step, but I'm pretty sure that you guys can see this. All right. So I have this integral. So let's see what can we do about it. Well, if you look at it, this is nothing else. It's the same thing. So if we just go back to the initial variable, so this is the square root of natural log of 3 plus x, if you want, over the square root of log of 3 plus x. Or the square root of log of 9 minus x dx. All right, that's great. That's beautiful. So this means that, so what did we get? So this means that all right, so this means that I will be nothing else than just 1/2 I plus I, right? We can write them in this way. Or if you want, this will be, we can write this as the integral of 1/2 times the integral from 2 to 4. We can add the integral by itself, and you'll see why I'm doing this. Well, it's pretty. So here we have log of 9 minus x, square root of log of 9 minus x, plus the square root of log of 3 plus x over the same thing. All right, dx. Great. But this is nothing else than, well, this integral will be 2 times, sorry, 1/2 times 2, which is 1. So our integral is 1. That's it. Pretty easy exercise, very standard. Well, well, you can actually generalize this. It doesn't, you can replace the square root of ln of x by any function, let's say f, such that f of 9 minus x plus f of 3 plus x is non-negative, is not 0. So you can do that. All right, so this is a very easy problem. Usually when you see this kind of a symmetric integrals, this is what you do. You take, usually you do the slight change of variable so that you can go back to the initial integral. All right, so that's was pretty easy. Let me give you another problem now. So this is, let's say this problem 1. Now problem 2. Which says the following. I don't recall the exact statement, but anyway, so let f be a function, hope I'm not wrong, be a non-negative actually, okay, be a non-decreasing function. Such that f of x, we have this condition, f of x is greater or equal than the integral from 0 to x of f of e to the power t dt, all x are negative. So we have this kind of condition. Show that f of x is actually 0. All x are negative. I hope this is the right statement. Let me just check a bit. I hope so. I don't want to make any mistakes. Yes, indeed. Is the let me take this because I have the statements here. Yeah, the statement is correct. That's the statement. All right, let's see. So usually when you have this kind of, and you have that the function is non-decreasing, so that's an important piece of information. So maybe we should explore that at some point. Well, of course, any monotonic function is integrable, so I don't have any problems with that. But now I will slightly, this goes back to, well, I know the function is non-negative. It's also non-decreasing. So this rings a bell to this basic fact that any continuous function on a closed and bounded interval that is non-negative and its integral is zero, its actual is the function is zero. So maybe I should modify that a bit. So maybe I should prove a lemma like that. So we should first we prove the following lemma. And this lemma says the following. So if I have a function, let's say g, defined on a closed interval a, b, real valued, satisfies the conditions so the first one is g is non-negative for all x in a, b, close at a, open at b. Pay attention, this will be crucial. G is non-decreasing. And the third condition I like to use is that the integral of g is zero. Well, guess what? The lemma says the following, that g is zero for all x in AB. Close at A. So that's the lemma. So let's prove this lemma. Well, the proof goes proof of the lemma goes in the same similar lines with the lemma when g is continuous. So let's assume by contradiction that g is not zero. So that there exists an x0 such that g of x0 is not zero, and without loss of generality, we can assume that g of x0 is greater than zero, let's say, such that that there exists an x0, right, with g of x0, let's say it's positive. All right, great. Well, since g is non-decreasing, let's write it in this way. Since g is non-decreasing, g of x is greater or equal than g of x0, and this happens for all x in the interval x0, b. Great. So this implies that the integral from a to b of f, of g, I'm sorry, which is zero, we can break this integral into two parts, from a to x0 and from x0 to b. All right, we're going to neglect one part, and I'm going to neglect this one here because the function is non-negative, the integral is non-negative, so I don't care about it that much. And so this will be greater than the integral from x0 to b of g of x dx. So, but this will be greater or equal than g of x0 times b minus x0, right? That's pretty obvious to see. And now let's be careful. This guy, we assume by assumption this is positive. Again, this will be positive, so the entire integral is positive. So we get the contradiction. All right, so the proof of the lemma is done. That's the proof of the lemma. And now we would like to use this lemma to solve our problem. So let's go back to our problem. So going back to the problem, for, let's say, x greater or equal than 1, we have the following. So let's use our condition in the problem. So f of x is greater or equal than that integral over there. So let's use that, and we're gonna use the same idea as in the proof of the lemma. We're gonna break the integral into two. So let's do that. So we have this here. And now I'm gonna write this, like I said, I'm gonna break this into two because I wanna, so this is from 0 to x minus 1 of f of e to the power t dt plus the integral from x minus 1 to x of f of e to the t dt. Now we should be careful here because this will be greater or equal than the integral from 0 to x minus 1 of f of e to the power t dt, and plus this integral here, if we look at it, if we change the variable, if you want, this will be greater than plus the value f of e to the power x minus 1, right? So the function is non-decreasing, so therefore we can we have this inequality. All right, beautiful. But now, why am I doing this? Because now by the elementary inequality, which can be proven in many ways, and I've used this plenty of times. So the elementary inequality e to the power y greater or equal than y plus 1 or y positive, we obtain the following. We obtain, so let's look at this guy here, the last. So we obtain that the integral from 0 to x minus 1 of f of e to the power t dt plus f of e to the power x minus 1 is greater or equal, and now let's be careful here. So this is the integral from 0 to x minus 1 of f of e to the power t dt plus, my function is increasing, so this would be plus f of x, right? Okay. But, so, the integral, we obtained that the integral from 0 to x minus 1 of f of e to the power t dt is negative for all x greater or equal than 1. All right, so we have this information, and I think we're in a good place at this point. Well, but we know that the integral is non-negative, right? If you look at this here, this is non-negative. We know this already. The function is non-negative. The integral is non-negative. So this implies that that the integral is actually 0. Right? And of course, by the lemma, well, 0. Oops. So by the lemma, f of e to the power t is 0 for all t positive, and therefore this implies that f of x is 0 for all x greater than 1. But since f is non-decreasing and positive, non-decreasing and non-negative, this will imply that f of x is 0 for all x non-negative real. All right, and that's it. That's exactly what we wanted to prove. So that was pretty neat. Like I said, the main ingredient was this lemma. So that was the life savior actually for this problem. I don't know if this can be proven in a much easier way, but anyway. All right. So that was problem number 27 in my list. Let's see. Problem 28. I'll call this problem 3 here. Problem, well, let's see what it says. It's a Putnam B1. Like I said, a pretty easy problem as well. 1990. Yeah, this is actually pretty standard. So it says the following. Find all real valued continuously differentiable functions f on the real line such that for all x, right? For all x, we have the following equation, functional equation, f of x squared. So the square of this function is this integral, the integral from 0 to x of f of t squared plus the derivative of f of prime of t, that's squared as well, dx plus 90. Oh. All right. So usually when you have this, well, I don't want to get into, you'll see more of these when this kind of integral, well, let's call it them integral equations, integral differential equations. We will do more of these. In fact, even much more complicated than this. This is pretty easy. You don't need to know differential equations to solve this problem. So first, let's see. Let's point out some trivial remarks for this problem. For example, if you put set equal x to be 0, for x 0, what do we get? So we get f of 0 squared is 90. So f of 0 in absolute values, the square root of 90. All right, great, because we will need this. All right, so now since we deal with the integral functional equation, okay, let me stick to this. Since we're dealing with a functional equation, and on the left-hand side, we have a function, we have the square root of a function f, and on the right-hand side, we have an integral involving the square of the function and the square of the derivative. So maybe we're in a good position since the function is continuous, then I don't have any problems by the fundamental theorem of calculus. In fact, this will imply that that the integral is differentiable. So I have no problems in differentiating term by term. So taking the derivatives on both sides. Let's call this star. In star. So we're taking the derivatives. We will have the following. So we will have, okay, let me write it like this. physics notation. Right, so all right, so this will go away. It's just 0. I don't care about it, about this one. So this would be 2 f of x times f prime of x. And now let's be careful here, because we take the derivative with respect to x of the integral. So this would be f squared of x. So by the fundamental theorem of calculus, so this is f of x squared plus f prime of x squared, the derivative, right? Or if you want to just, this is nothing else than just f of x minus the derivative of x squared is 0, right? Great. So this implies that since this is non-negative, right? This is 0, so this implies that f of x is equal to the derivative, to its derivative. All right, so this is the first order differential equations. We'll solve this, but you can actually divide by, well, I'll leave it to you as an exercise, that the solution for this is that f of x will look like this. It's a constant c times e to the power x. So these are the solutions to this equation. This, let's say, first order differential equation. So these are the solutions. But you can solve it by hand. Very easy. You can just, you can recognize the logarithmic derivative there and so on. All right. So now we need to find who is this c. We need to find this constant c. Well, that's not hard to do. Well, let's see, how do we find these c? So again, we go back to the initial observation that for x equals 0, we got that the square root, the square of my function f evaluated at 0 is 90. So for x equals 0, f of 0 is c times e to the 0. So it's c. So this means that c is what? Is plus minus the square root of 90. So the functions we're looking for, we are looking for are given by f of x is plus minus the square root of 90 times e to the power x. So these are the functions. And you can easily check that they verified this equality, they verify star easily. So, well, when you have a functional equation like this is how you solve these kind of problems. Like you take, when you have a function, in fact, we did an example in one of the lectures, if I remember correctly, much more complicated example than this one. So usually that's the strategy. You take the derivative and see what happens there. All right. All right, I think I have 2 more problems to go. So the next one is the following. This is problem 3, problem 4. This is a very nice problem, though. And it says the following. So it's in more or less in the same spirit as problem number 2. So let's just consider a function f defined on 0, 1, and with values in 0, 1, but open at 1, be a continuous function such that the following rather, well, weird condition holds. The integral from 0 to 1, well, I would say it's very artificial, of x to the power n dx is less or equal than the integral from 0 to 1 of f of x to the power n dx for all n greater than 1. Show that f is 0. All x is 0, 1. This is a pretty standard problem now, but it has a very nice idea though. So you see we have an and there, so maybe we could use some kind of a limit argument. But first, I need to look a bit at this function because I need to make some observations. You see, this inequality seems, this integral inequality seems a little bit artificial, right? Because we have x to the power n inside the argument of f, but then we have f of x to the power n. So there might be a temptation for you to use some kind of weird integral inequalities, but I can assure you at least that this kind of approach will not work, will not be successful. So maybe we should think of something like to have in mind a similar lemma, because since we're trying to prove that the function f is 0, so maybe we know it's continuous, maybe we should invent ourselves some kind of a non-negative function, which, in fact, this is non-negative already. So it's continuous. So if we prove that the integral of f is 0, then we're done. So maybe we should do that. We're done. Right? So let's prove that. So how should we prove this? Well, we know that the function is continuous, right? So we cannot, it's on a compact interval, so we know it's bounded, and moreover, it attains its bounds, right? So we know this from Weierstrass theorem. All right. But first, I'd like to make one observation, which is trivial, because this will be good when we deal with the change of variables. Because you see, the idea is that I have this guy inside here, x to the power n. So maybe I should perform a U sub. Maybe I'll denote this x to the power n equal by U. Yeah, that would be an idea. But first, let's observe that if we multiply x to the power n minus 1 by f of x to the n, this will be less or equal than f of x to the n, right? For all x in 0, 1. That's obvious. So that's the one thing that we should state as obvious, right? And now integrating this inequality, so this last inequality, let's see, what do we obtain? We have that the integral from 0 to 1 of x to the power n minus 1 f of x to the n dx is less or equal than this integral. All right, beautiful. But the funny thing, now we use the hypothesis, this will be less or equal than the integral of f of x everything to the power n dx. Right? And of course, this will be less or equal if you want. Then, since we said that f is continuous on a compact interval, it's bounded, and moreover it attains its bound. So this will be less or equal than m to the power n, where m is nothing else than just the supremum of f. And this supremum is less than 1. Just look how the function is defined as it has values in 0, 1, and open at 1. So this is less than 1, and this is very important. So now we have this inequality. Now we can perform the change, the U substitution. So so by the substitution, x to the n equals u. What do we get? So we have that n x to the power n minus 1 dx will be du. That's exactly what we need. So this will imply, and this finally implies, wow. Implies that, well, this is also non-negative. Let's keep that in mind, that 0 is less or equal than 1 over n, the integral from 0 to 1 of f of u. The u is less or equal than m to the power n, or if you want equivalently, we have this inequality. Now we can use a squeeze theorem. This happens for all n. 0 approaches 0. This thing, I'll leave it to you as an exercise to show that this will approach 0 as well. So if you have a number between 0 and 1, and then the limit, the limit of a constant between 0 and 1 to the power n is 0, but moreover, even if you multiply by n, is also 0. So by the squeeze theorem, this will also approach 0. So here, squeeze theorem. The integral of f of x dx is 0. And the conclusion follows. That was a nice problem. So you see, we didn't use too much, just like some smart, well, obvious inequality, and then we integrate it and change a variable in squeeze theorem, that's it. So it was in the spirit of problem 2. I would say this was a bit easier. And now I would like to, in the remaining time, just to do one more problem. In fact, it's inequality, but I was thinking of saving this for next time, but maybe not. So this was problem 5. And again, this was a Putnam problem. Let me see. Statement. So this says the following. This was a Putnam B2 in 1996. All right, great. Prove the inequality for all positive integers n. And it's a double inequality. It's a pretty nice inequality. 2n minus 1 over e, everything to the power 2n minus 1 over 2, less than 1 times 3 times 5 times 2n minus 1, and this is less than 2n plus 1 over e, everything over 2n plus 1 over 2. Okay. So usually when we have this kind of problem, you try to, well, you see you have a product, we have power, so definitely we should take the log. And maybe Well, at first looks like a very innocent inequality. There are no integrals involved, but well, it's actually there are integrals involved here. And in fact, we'll make the following observation, which will turn out to be crucial for the solving this problem. All right, so we'll do the following estimate. So all right. So we showed that the integral from 1 to 2n minus 1 of natural log of x dx is less than 2 times log 3 plus log 5 plus plus log 2n minus 1. And we also show that this is less than the integral from 1 to 2n plus 1 wait. Of no, sorry, 3. The 3 of log of x dx. Oh, we show this inequality. All right, so the way we show this is if you look at this function log x, right? And if we draw the graph, oops. So you will see something. So if I draw the graph of, so here is 1. So if I draw the graph of y equals natural log of x, and if I approximate these rectangles here, right? Let's say this is 3, this is 5, this is 7, and so on. And at some point, I'll have a rectangle here. Oops. Something like that. So here I have 2n minus 1. And here, let's say I have 2n plus 1, whatever. All right. So the left, if you look at the left inequality, so the left inequality right, follows from the upper estimate of the integral by the Riemann sums, right? Follows from the upper estimate of the integral by Riemann sums. And why is that? Well, if you look at it, because the areas, if you look at the areas of each rectangle, or so the areas, so let's say because the areas of the rectangles are, so the first one will be 2 log 3, 2 log 5, and so on. 2 log 2n minus 1, right? Well, now if we, so that will be the upper estimate. But now if we look the lower estimate, so similarly, if we look at the lower estimate, of the integral by Riemann sums, well, this gives you the right inequality, right? Is pretty much the same thing. So we can look in the sense that, okay, let me draw it again. So we'll have here I have 3, 5. So here I have 1. Again, the function. So I can look like this. Right? So now the only thing we need to observe is that, but if we compute the integral of ln of x, the integral of log of x dx by using integration by parts, and we'll leave this to you as an exercise. It's pretty standard in calculus too. This is x log x plus constant, right? Wait. Sorry. Minus x, I forgot about it. Dang. Plus constant, right? Just integration by parts. Enjoy doing this. Well, basically we obtain our inequality. So basically we obtain our inequality. So in other words, we have, what do we have? So we have, so we have this inequality, right? Let's call this star. So basically, once we integrate this, we obtain our, we want to show that this is equivalent. This is basically the conclusion. So let's do some computations here. And if we look at it, in fact, I would leave it to you to show that star is equivalent with the conclusion of the problem. I'll leave this to you as an exercise, right? It's just basic algebra, so just basic operations with the logarithm and exponential. All right, guys, I think I'm going to stop here for today. Well, this was the first recitation. As you can see, the recitations are usually shorter, and we solve only problems. And the next recitation, if I look at we will deal with more with integral inequalities. And in fact, there will be a special recitation where I will solve I will discuss a problem, a Putnam problem, and I'll, well, you'll see. I'll leave it to you as I say, surprise. You'll see plenty of solutions basically for that problem. And yeah, that's what we're going to talk about, integral inequalities, more about integral inequalities next time. All right, thank you very much. Bye-bye.